All right. I guess everybody can see
Perfect.
this.
Perfect.
Yeah, good. Uh, the two books that I'm working on, actually, I just submitted the manuscripts from both of them to the publisher. One is called The Essential Nature of Time, and the second one is The Essential Nature of Black Holes. So these are sort of introductions to what these two topics are. Lots of good, weirdness in each topic area. I'm not sure if they're going to be printed in time to be stocking stuffers or whatever your holiday tradition is. Uh, some people don't use stockings as part of their traditions, and I respect that. uh, so anyway, yeah, I'll probably let you know in November whether or not they're going to be available. I'd like to think that they are because I'm delivering the manuscripts about 3 months in advance. So, maybe they do have time. Anyway, okay. Heliophysics, big year. Uh, Heliophysics, first of all, you're not going to find heliophysics in the dictionary. So, at least for the foreseeable future, anybody that talks about heliophysics to the public is going to have to define what the term means. Well, it's a combination of helio, which is the sun, and physics, which is physics. So you got to expect that with a word like that, it's talking about something that has to do with the sun and physics. And there are a lot of things that go on in the sun that have to do with physics, believe me. It produces electromagnetic radiation and gravity. It's a giant ball of plasma, has a lot of matter, all kinds of good things. And it's got things like sunspots and coronal winds and coronal mass ejections and solar wind. So there's a lot of good stuff that comes out of the sun that's potentially of concern to the Earth and our technology. And so heliophysics is sort of the primary science discipline that studies all the ways in which these different phenomena happen, what causes them, how they're related to each other, and ultimately at the core of the sun, where the energy comes from and how it gets delivered to the surface so that we can actually see light. So it's that kind of a subject. That's why we use the word heliophysics instead of some other very long concatenated word that describes the sun in a more complicated and detailed way. The heliophysics big year was an idea that came up, I guess it must have come up last summer as a way of getting people sort of interested in the sun. We have a couple of bookend events that went on during 2023 and 24. The first of these was the Ring of Fire eclipse last October, which was extremely spectacular and millions of people watched it. We also had the recent April 8th total solar eclipse. And then finally, next December, which is coming up fast, we're going to have the close approach of the Parker Solar Probe to the sun's surface. And so between October 14th, 2023 and December 24th, 2024, we had 14 months where we could actually do something interesting. And so Nikki Fox, who's now the director of science at NASA, she came up with the idea, well, let's concoct a kind of a human interest theme behind each one of these months. So, one month was called the month of fashion, sun fashion. Another would be sustainable energy, and so forth and so on. Well, the themes are really great, but I thought that, hey, I'm going to do one better. For each of these themes, I'm going to create a mathematical set of problems under each of these themes. And so I started thinking about this last summer, and I said, oh, sure, yeah, no problem. 14 months, I can crank out 3 interesting math problems per month, no problem. Well, for most of the months, that was not a problem. But there were a couple of months whose names shall not be mentioned, where I was pulling out my hair almost a week before I was supposed to deliver the webinar. And I finally came up with some math problems that seemed to be okay and sort of made sense. uh, One of my months that I had trouble with was the month of fashion. Well, there were a couple of things that I could have done, but instead I decided to take the perspective that fashion has a lot to do with color. I mean, for the most part. And so I decided that that would be the month where I would talk about how filters work, how color works, and go forward with that. And that turned out to be okay. This month is actually a mirror of the one that I did last January, where I talked about solar energy. Because with this month, we're talking about environment and sustainability. Well, uh, certainly the sun can sustain its environment indefinitely. So I realized that that wouldn't necessarily be the focus of a topic like this. So what I decided to do was to look at how humans use solar energy and convert it into electricity as a way of moving away from a fossil fuel civilization to one which is actually environmentally friendly and sustainable. So this month I'm going to talk about solar panels, but with the caveat that by the time we're finished with this talk, you're probably going to be able to put up your own solar power system on your own house because the mathematics is fairly simple, but there are some interesting gotchas that go along with it. Anyway, so the heliophysics big year is connected with heliophysics big questions. NASA likes to look at each of its four topic areas: planetary science, earth science, astrophysics, and heliophysics. And under each of these topic areas likes to think about its research and engineering in terms of three big questions. Well, for Helio, the big questions turned out to be: what causes the sun to vary? How do the Earth and the heliosphere respond? And what are the impacts on humanity? That works really well, but if you're a teacher trying to teach these sorts of subjects and in answer to these three questions, you'll find yourself sort of lost in a very large container of quicksand. So what we have done at NASA HEAT is to create what's called a framework for heliophysics education. We've basically taken these three questions and broken them into three subsidiary questions that connect more intimately how these questions are related to the national science standards. So tonight, what we're going to do is look at a particular standard. The sun is the primary source of light in the solar system, and that connects up with Physical Science 1, Physical Science 2, and Physical Science 3 in the national science standards. And so that's going to be our focus this evening. And so we're going to start that by looking at solar energy. Well, sun is a very powerful source of solar energy, hence the name solar energy. And for most of human history, we've sort of relied on the sun to provide us with light and heat, and it gets modulated by the rotation of the sun, the orbit of the sun, and the tilt of the rotation of the Earth, orbit of the Earth, and the tilt of the Earth's axis into seasonal variations. Okay. Well, we're not going to talk about seasonal variations tonight because, quite frankly, I find them rather boring. Anyway, sorry, oops, putting too much of my own opinions into this talk. What we do, however, have is a civilization that relies increasingly on the generation of electricity. Electricity is sort of a common currency that we now use, and we use it to run motors, to do all sorts of different things, foundries for smelting iron, and you name it. So ideally, we want to take whatever primary energy sources we have and convert them into electricity, which we can then use to do a variety of things that have nothing to do with the original source. And to make this work, we've created a technology. It actually was created initially in the late 1800s, sort of by accident, It's called a solar panel. It turns out to be a special type of silicon that when you bombard it with solar energy, that is to say visible light, uh, the, the silicon actually produces streams of electrons, which can then be collected as a current, and the current can be collected to store electricity in a battery, and so forth and so on. So solar panels, were a great scientific toy in the late 1800s and the early 1900s. But they really weren't used for much because they were kind of a novelty, and nobody could really figure out what to do with them. And at least the original solar panels were so inefficient that compared to coal-fired power plants, which were the rage in the late 1800s, they just didn't produce enough to be of any consequence. However, once we got into the space age, it turned out that being able to generate electricity with solar panels on a spacecraft was almost the only way that you can create energy to run a spacecraft in space. You couldn't do it with batteries because batteries, when you run them through the kind of heating and cooling cycles that you get in space, they would dissipate their electricity very, very quickly and not be usable for very long missions. So it came to be realized very early with the original Telstar satellite and others that they would cover them with solar cells, solar panels, so little tiny quarter-sized solar panels, and generate the electricity needed to run the transmitters and the receivers and whatever else equipment that was necessary. That became big business starting in the late 1950s, and we've sort of we've ridden this tide of improvement in solar panel technology for the last 60, 70 years now. It used to be that you could only convert about 1% of the visible light falling on a panel into direct electricity. Now that number is upwards of 60% with some of the newer technologies. Moreover, modern solar panels used to be very stiff, very brittle. You had to cover them with glass, like these inexpensive solar panels that were very common a few decades ago. Now we have flexible solar panels that are even being looked at as things you can add to somebody's clothing to run. I don't know what you would want to run on a piece of clothing that with a solar panel, but in principle, you could do that. Yeah, you could charge your smartphone with your own solar panel that's woven into your clothing. You could use it to run novelty lights and signs on your back. I think one of the first applications of that technology is going to be the "Kick Me" sign. I'm sorry. You never went through that in school, did you? Having somebody post a sign on your back that says "Kick Me." All right, never mind. Okay, but now you can do it in LED lights run by solar panels that are woven into your clothing. All right. So, as I said, solar panels are the workhorses of NASA satellites and communication satellites in near Earth orbit. Just about every satellite that you see, if you go and Google, satellites, you will see some kind of a solar panel hanging off the side of the satellite or spacecraft. Another application in the inner solar system is that there is so much sunlight in the inner solar system that you really don't need solar panels that are very big in order to collect kilowatts of electricity. By the time you get out to the orbit of Jupiter, however, sunlight is about 25 times fainter. So that means that you have to increase the area of your solar panels by almost 25 times in area in order to collect the same number of kilowatts that you did in Earth orbit. So there's a penalty that you pay if you try to use solar panels everywhere in the solar system, and that has all to do with the inverse square law and the diminution of sunlight the farther out you get. That's why when we get beyond like the orbit of Jupiter, the favored technology is to use radioisotopic generators, which use decaying radioisotopes to generate electricity by essentially using the heat produced. Even more modern technologies that are going to be tested in the next 5 to 10 years are going to involve small nuclear power plants put into space. Now, why do you need all that electricity in space? I mean, we've been able to run a lot of good science just using the panels that we have, which are fairly modest in size. But the really cool thing is there's a whole technology for propulsion called ion electric propulsion. And that requires lots and lots of electricity. And that typically is produced by using solar panels. And so in that case, the more electricity you generate from the solar panels, the more thrust you can get from these electric engines. So that's sort of the direction that propulsion is going to go using solar panels. Anyway, what I'd like to do is to sort of talk a little bit about practical uses of solar panels. And the first thing that you have to think in terms of is solar power math. It's a little bit funky, but not too hard to really think about much. A typical house, that runs electric air conditioning systems and home entertainment systems and things like that requires about 30,000 watt hours. That's called 30 kilowatt hours of electricity. Now there are 24 hours in a day, so if you divide 30 kilowatt hours by 24 hours, you get about 1,200 watts. That's constant electricity that you have to be able to produce all the time in order to run your house. The average cost of electricity is about 16 cents per kilowatt hour. So the question is, well, for a typical home that runs at 30 kilowatt hours, how much does that cost per day to run that particular house? There's also another factor that's of interest, and this is the environmental impact and sustainability, and that is how much carbon dioxide emission per kilowatt hour is produced. If you burn coal, there's one particular figure for that. If you are a fully electric house, that CO2 emission per kilowatt hours is a savings. That's a statement of how much you are not putting into the environment because you're using electric power from a solar panel. So that's the direction you want to go. You want to use solar panels as a competitor to coal and oil and fossil fuels. And you want to figure out what the savings is if you go completely electric with solar panels rather than using fossil fuels. And then the bottom line question is, how much is it going to cost to run this house for a year, and how much CO2 is produced typically? So the actual calculation is pretty straightforward. You start with the house at 30 kilowatt hours. We just said that it's 16 cents per kilowatt hour. So 0.16 times 30 gives you about $4.80 per day, or about $1,700 per year to run your house, if that's the cost of your electricity from your utility. The cost in utilities varies anywhere from like 14 cents, as high as 20 cents, depending on your location, the rate structure of your utilities, and any number of factors. But roughly, it takes about $1,700 a year to run a typical house that consumes that much electricity per year. Per day, sorry. In terms of the amount of carbon dioxide emission, we know that number is about 1 kilogram per kilowatt hour for fossil fuels. And so if you do that multiplication, 1 kilogram per kilowatt hours times 30 kilowatt hours per day, you get 30 kilograms per day, or about 5.5 tons per year. So a typical house is responsible for roughly about 6 tons of carbon dioxide every year. And that's an environmental problem, because that's what contributes to global warming, through the greenhouse effect. We're not going to talk about methane gas because that isn't part of this energy structure for generating or conserving on methane gas. Methane gas is about 40 times more effective in polluting and producing greenhouse problems than CO2 is. So we're not going to go there on this particular problem. So a typical solar panel for homes generates about 40 watts. That's one of those little square or rectangular panels you see being installed on this house. But here's the problem. You know, we want to have, I said, 1,200 watts of electricity. The panels are 400 watts each, but there are only about 5 sunny hours each day where you can actually collect electricity using the solar panels. During the other hours, it's either nighttime or the sun is so low on the horizon that it's not producing enough light to really activate the panels very efficiently. So the question is, you know, how many panels do you need to generate the 30 kilowatt hours to run your house every single day? That calculation looks something like this. We've got 40 watts times 5 hours. That's 2,000 watt hours or 2 kilowatt hours per panel. But you need 30 kilowatt hours to run your house. So if you divide these two numbers, you need 15 panels. All right, that'll do the trick. That'll allow 15 panels to accumulate at 40 watts per panel enough electricity during the good sun generating times of the day to last you from sunrise to sunset. Of course, at nighttime, you have another requirement because the sun isn't around. So some of that 30 kilowatt hours that you need per day, you know, has to be used at nighttime. So that's why all solar panel systems have batteries associated with them. Because during the daytime, you'll have enough panels on your roof to generate in 5 hours all of the electricity that you need in a full day. But if you're only using a little bit of that, the rest of the electricity you're generating goes into charging up your batteries during the daytime. So at the end of every 24-hour cycle, you've completely discharged your batteries, you're waiting for the next sunrise, sunset cycle to happen, and then during that period, you generate enough surplus electricity to once again charge up the batteries to full potential so you can use electricity at night as well. So it's a little bit of a kind of a balance between the two. You have to size the panels against your rate of consumption in the house and also the size of the battery that you can afford to install to store the excess electricity for the evening operations. Also, the installation cost, it costs about $9 per watt to install one of these panels. So working out those numbers, we had 1,200 watts of electricity is what we're looking at, and it's $9 a watt. So we're talking about $10,000 to install one of these 15-panel rooftop solar systems. That typically will include a battery for off-peak charging, and also the labor charges, the manufacturer charges, and everything else. So for $10,000, you can run your typical house. Typically, in most states, and the federal government has subsidies that will cut that number down by factor maybe $4,000. There might also be state programs that will cut that down even further. So at the end of the day, you might be able to build a system like this for about $6,000, $7,000, give or take. I mean, you can figure out, the investment of the solar panels that you've installed in this system and compare that to paying 16 cents a kilowatt hour for daily electricity throughout an entire year. And you'll find that generating your own electricity is far cheaper than using the power grid to supply it to you. And it's also green because you're not producing carbon dioxide as a byproduct of your production. So anyway, there are many places where you can go online to find out how to calculate costs and things like that. And I'm just showing you one of these examples down here at the bottom, evergreensolar.com. They have many places have actual calculators where you give them your latitude, longitude. They figure out, how much electricity you can generate and off and running. The deal that we're looking at, for sustainability and impact is carbon reduction. If you install solar panels and become 100% green, you save about 6 tons of CO2 production every year. And over the 30-year life of the solar panels, that's about 180 tons of CO2 that you're not putting into the environment for your children and grandchildren to worry about. So that's really a good deal. One question that you might have is, well, once you install the panels, then you get, all of this wonderful reduction in CO2 because you're not burning fossil fuels anymore. But, the question is to manufacture those solar panels, in a company, in a foundry, in a lab, whatever the venue is, are they producing CO2 in order to create the panels that you are now using? You can actually work this out as well. The mining and melting of silicon releases about 50 grams per kilowatt hour. All right. That's just the mining to get the base products for creating the solar panel. The rest of the steps don't involve the production of CO2. It's really only the mining and melting of the silicon into usable forms that really is the big generator. And for your home, this is a one-time cost. I mean, once you've installed your panels, the panels have been manufactured, and so it's a one-time thing. You don't have to keep paying this 50 grams per kilowatt hour over and over again. So the question is, how many kilograms of CO2 was released in creating the 30 kilowatt hour home power system? That basically is just a straightforward multiplication. We have 0.05 kilograms per kilowatt hours, that's 50 grams, times 30 kilowatt hours, and that gives us about 1.5 kilograms. That 5 is hidden behind pictures of you guys, so I assume that's a 5 in red. And so we have to tack that on to the 180 tons that we saved by actually running the solar panels and generating our electricity. So you can see that the startup cost, the manufacturing cost of these panels is 1.5 kilograms compared to 180,000 kilograms. So it's negligible and you don't have to worry about it. Now, there are other situations where this calculation really does have to be done carefully. For instance, the manufacture of an electric vehicle. That involves many industrial steps. Many of those steps produce CO2. And so you have to go through the entire supply chain, how they manufacture the components, get the number of grams per part of CO2 that was contributed, and then add up the whole shebang. And quite frankly, I don't know where that number winds up because I've never seen anybody actually do the complete supply chain CO2 production for producing one electric vehicle, which you're going to use and not burn fossil fuels any longer. That's an interesting question. So maybe I'll give that to one of you enterprising folks to go in and research yourself. And it's going to be like stamp collecting. First, you have to identify what all the parts are that go into an electric vehicle, the major components. You have to find out who manufactures them. You have to find out, how they do the manufacture. And, it'll take you a long time, believe me, to do this, but it might be worth it. You might actually be able to publish it somewhere. Anyway, the end-to-end calculation of CO2 input into the atmosphere for any product that we manufacture is a very, very real calculation that people do. I'm just showing you a very trivial example because solar panels are now going up on rooftops everywhere. And so this is a number 1.5 kilograms for a solar panel for a 30 kilowatt hour system. It doesn't sound like much at all. Anyway, here's some advanced problems. We're gonna add in the calculation for electric vehicles in this case. A typical car burns fossil fuels and produces about 44 tons every 10 years of emission. An electric vehicle on a battery and for typical driving saves about 44 tons of CO2 every 10 years because gasoline is not being burned. Now, the thing is, that sounds all great, but the thing is that you have to charge the car up. You have to charge its battery. Two ways you can do that. You can use fossil fuels to generate the electricity to charge up your EV battery, or you could plug your car into your house, which is now fully equipped with its own solar panels. So now the charging up of your electric vehicle is green. Your use of the solar panels for your home electricity is green. So this is the best of all possible worlds. So we'll take a look at some of these numbers here. An electric car uses about 20 kilowatt hours of electricity per 62 miles on average. You'll produce about 1.8 pounds of CO2 each 60 miles if you fill it up using solar power. And if you use basically coal-powered electricity, it's more like 44 pounds or 20 kilograms for each charge up. So we can calculate over the course of 10 years, which is the typical life of an electric vehicle. Coal-powered charging, that's 12,000 miles per year. And you work through 10 years times 12,000 miles per year divided by 60 miles. Because in the charging question, I said it's 1.8 pounds of CO2 every 60 miles. So I have to take the 12,000 miles divided by 60, and that gives me the number of pounds per year. And then I get 10 times that for 10 years. And 44 pounds is basically what you get for fossil fuels. So the bottom line calculation is for coal-powered charging, for a typical EV, it's going to be about 44 tons per year to charge that electric vehicle. So that's not a very green situation. If you do it by solar powered charging, it's only 1.8 tons. So clearly, solar powered charging of your electric vehicle, that is to say, plugging it into your house, is a more green solution. Well, it makes sense. I mean, you could sort of figure this out, but here are the numbers that sort of go along with your intuition about whether coal-powered charging or solar-powered is better for a green situation. So anyway, in 10 years, the net savings is 44 tons, which is what you're saving from charging the electric vehicle with solar power, minus 1.8 tons, which is basically the penalty you pay for using a solar system. I don't really want to go into the details of that. And so basically you're saving 42 tons of CO2 every year if you charge your electric vehicle with a solar electric power system on your house, which isn't too bad. Not bad at all. And that's a 10-year number. Compare that with 180 tons if you ran your entire house on fossil fuels. So, if you add 180 tons to 42 tons, you get to 222 tons of CO2 savings if you're an all-electric solar-powered house with an electric vehicle. So that's now starting to look like actual money and a major savings to the environment if you do it in that particular way. Now, here's a more advanced problem. I mean, moving away from the single house model and the single EV model, let's take a look at, for the United States, you can actually work out how many megatons of CO2 are saved if houses go solar, and you can calculate every year how many houses are going solar in the real estate market. Those numbers are available. And you can also see what the percentage growth is of that. That's a number that is pretty well known. You can also do the same calculation for the CO2 savings from electric vehicles in megatons, and that can be modeled by this equation. X in each of these quadratic equations represents the current year minus 2025, because essentially what I did is I took the data that I got online for each of these two cases, and they would generally give forecasts that start in the year 2020 and go out to the year 2050 or 2100. And so I just did the portion starting in the year 2025, going out to 2050 or 2075. Just as an approximation. If you do this, you can plot these two functions using Excel or a graphing calculator. If you set the home CO2 savings against the electric vehicle CO2 savings, that basically is putting one of these quadratic equations equal to the other. In the left-hand column, you kind of step your way through the solution to the thing. And so X is 5.8, and that's the current year minus 2025. So that means the year 2031 is the year when the savings from homes going solar matches the savings of cars being charged by solar electricity. Okay, so that's kind of interesting. We're kind of on the cusp of when that's going to happen, given all these approximations that are going on in this thing. You know, we're getting to the point where people investing in electric vehicles and driving them and not burning fossil fuels is going to be as much of a savings as homes that are currently on the market or being planned to go fully electric with solar panels. And after that, the savings for electric vehicles is going to outpace the savings from home electric systems, mainly because the pace at which we're buying electric vehicles is going to be mandated that all new vehicles have to be electric, and that's going to come out in roughly the year 2030, 2035. So you won't be able to buy fossil fuel powered cars anymore. And if you want to still drive around the United States and visit grandma, you're going to have to buy only an electric vehicle. So that's going to really push the sales of EVs up, and the rate at which the savings is going to increase is going to, it won't become exponential, but it will definitely become an interesting power law relationship. Now, this is what you could do, you know, if you wanted to do things by hand the long way. You know, this is good math. It's always good to find the intersection of two quadratic equations. That's a good algebra 2 skill. But you know, we could also ask ChatGPT to do this. Have to phrase it a little bit differently. You know, we would phrase the query as H equals that equation and EV equals this equation, and for what value of X will EV and H intersect? Show your work, evaluate to one significant figure. The abbreviated ChatGPT response that I got was the following lines. If you set H equal to EV, which is what we did longhand in the previous foil, you simplify that to whatever that is, take the square root, and it left the answer as plus or minus 10 divided by the square root of 3. Well, I don't know how you feel about square roots. They don't come very natural to me. So basically converting that into a decimal, you get 5.77. And of course, the root that is physically reasonable is the positive root. So X is plus 5.8 to one significant figure. And that's precisely what we got when we did it longhand. So what I demonstrated here is sort of two things. One, you can use ChatGPT as an intelligent calculator. Okay. The other thing is that the answer for this very restricted problem will actually be correct when you check it by hand. Now, you can't guarantee that that's going to be the outcome for any mathematical query that you ask ChatGPT. So, let the buyer beware. It's going to be fun to use ChatGPT to do math problems, but you have to make sure that the particular type of math problem is one that ChatGPT is going to give you an accurate answer for. And for the last, well, for all of the previous webinars that I've given, I always have a ChatGPT version of the advanced problem, and I see how well it performed compared to having done the problem longhand. I'm only learning how ChatGPT works as a math calculator, and this is one fun way of doing it with some applied problems that are kind of interesting. But anyway, that's it. Next time, we're going to talk about solar cycle and solar max. We're going to talk about a number of different things, and in particular, the bottom line is, from what we are going to learn about the sunspot cycle and the cosmic ray cycle, when would be the best times to launch a manned expedition to Mars in the next 50 years. So that's going to be kind of the hard and fast practical answer at the bottom of these sort of calculations. Anyway, so the slides are available at this link, and previous webinar recordings are at that link on YouTube. And I think I'm now going to stop sharing and entertain any questions you might have. Okay, well, it looks like we got a few more people logging in. That's nice.
Yep.
Unfortunately, they logged in late and they didn't hear all of the good one-line jokes that I made at the warm-up. So you'll have to come back next time for those. Anyway, questions?
Have a burning question? There have been some questions in that I was able to answer because I've had solar panels on a house, and I've just rented a EV.
All right.
But then, does anybody else have a question they'd like Sten to answer, a live one? You can say it out loud or put it in the chat. Shivam, are you unmuting so you can ask a question? Okay.
The suspense is killing me.
Well, let's, Matt raised his hand. Go ahead, Matt.
Hi, I'm just thinking more of EV is more better than carbon dioxide. Is it possible to make more EV better than making more carbon dioxide?
Well, the real kicker for electric vehicles is the manufacture of the lithium battery. That requires extensive mining, extensive purification of various mineral deposits, and that all produces CO2. The actual welding, and manufacture of the frame and things like that are not quite so CO2 intensive. So really, it's the battery. It comes down to the battery. The battery is very heavy. You need a lot of lithium to, create the battery process. And if we could come up with something that's lighter weight than a lithium battery, but packs as much energy, that's the direction that technology would have to go to further reduce the CO2 from the manufacture of electric vehicles. So. I'm 70 years old, so I'm not going to worry about that. I'm going to put that on the table for all you young whippersnappers to figure out.
I just heard I saw a quick story about there's been a huge discovery of lithium, I think, in Wyoming.
Yeah, it's any place where you have, salt flats, dehydrating water, mineral deposits like that, or even, geologic deposits, fossil deposits of inland sea material. I mean, you're going to find lithium, up the wazoo. There are some really sketchy places that are being mined right now. There are places in the Rockies where indigenous people have, sort of special areas that are holy to them or very culturally sensitive, and they are also places where there's a lot of lithium mining planned. So there's a lot of unfortunate confrontation between, various groups. But again, if we can find an alternative to lithium batteries, I mean, that would be miraculous. And there are actually several that are in the lab right now, because lithium batteries are scary as hell. You know, it's they have very high energy density, but my God, if you heat them up or you short them, they blow up like a little bomb. And they sometimes do that spontaneously without you having done anything to provoke the situation. So lithium is, for safety reasons, a direction that I'm sure is going to be de-emphasized in the very, very near future in favor of other technologies that are more safe and energy efficient.
Well, KM had a question about that in the chat. Why not just put the solar panels on the car?
You would need too much area of solar panel, plus you can't drive at night, right? Which might be a good thing. We should return to our roots as ancient mammals who only actually do anything during the daytime. But,
or maybe just have a car that runs on kitchen waste, like in Back to the Future.
But kitchen waste is organic, and that produces CO2 under combustion. So you're not buying anything that way.
Other questions? Matt, do you want to chime in and ask your question about the perihelion before we say goodbye? Scrolling up. Something about a Venus flyby after the perihelion?
Yeah, very likely. I mean, after this coming December, I mean, there are still another 5 or 6 orbits planned for the Parker Solar Probe, and if it gets funding for an extended mission, which I'm sure it will, then there'll be dozens of orbits after this December. So, we're going to be hearing about Parker, at least through, 2028, I would think. It's very, very hard to shut off a scientific satellite that's returning really productive data. We all talk about a nominal life of 3 years. Nah, never happens. It turns out that our engineering technology is really, really good. So these spacecraft that we say are only going to work for 3 years, for the Voyagers, they've lasted, 40 years now, and they're still going.
Remarkable.
Yep.
Let's see, we have another message here. Oh, any other alternative method for harvesting electricity?
I really love the expression harvesting electricity. There's something about that sounds organic. You know what I mean? And that's really what we should be doing. We should be going out there in the field, and picking solar batteries off of stalks of wheat or something. I don't know. But no, yeah, I mean, there are other technologies that are being looked at. I mean, there are the chemical batteries, all right, which, chemistry. There are, nuclear types of batteries. There are batteries that involve, well, not batteries, but electric energy production that involves capturing energy from waves crashing on the shore. Not terribly practical for electric vehicles, but probably practical if you have a centralized energy generation plant that uses wave power and then distributes that to homes to use to charge their vehicles. That could be very green. And then there's just getting a gallon of green paint and painting everything that looks like it's CO2 production, and just everything is green. So I'm sorry, that's a really bad joke. But yeah.
Is that called greenwashing?
Yeah, it's greenwashing. Yeah. Yeah.
Say it's good, even if it is.
I actually thought that was pretty good, but all right.
Not bad.
All right. Any other questions? Next time we're going to talk about the sunspot cycle and cosmic ray cycle, and how often Mars is closest to the Earth. And by combining all 3 of these, we're we're going to discover that we're never going to be able to go to Mars. No, actually, there are going to be some windows where we can actually scoot over to Mars if we can get there, within a few months. And by the time those windows open up, we're going to have nuclear thermal propulsion or nuclear electric. And we actually will be able to get to Mars within a few months instead of 3/4 of a year, which is going to be very exciting. And stay tuned. Yep.
All right. Well, thank you all for coming. I will send out the information about the recording and the slide deck. And
Okay.
then I'll also send out the flyers for October, November, and December, so you can distribute them to your friends and family. And we hope to see you next month.
All right.
Thanks, Sten.
This is a very select group, by the way. I'm trying to keep this group really small because you're getting really good information, right? And so,
and asking
anyway.
really good questions. So
they're asking really good questions, yeah. And I think my answers are mostly correct.
Okay.
All right.
All
See
right.
you next time.
Thanks, everybody.